It is given a graph of some function f of x, and we need plot, or actually sketch a graph of 1 over f, a derivative, and the second derivative of this function. So let's start with the reciprocal 1 over f. How to do that? We can start with zeros of a function, because 1 over 0 is infinity, so there will be vertical asymptote. So we can see that at x is 1, there is 0 over function, so it will be a vertical asymptote of the reciprocal, and at 3 also there will be a vertical asymptote. So let's consider this part. We can see that this tail goes up, so y tends to plus infinity, so y becomes very large and positive. 1 divided by very large positive will be very small and positive, so this tail will falls on x-axis, or there will be an asymptote, horizontal asymptote, y is 0. And we can see that when we tend to this point from the right, y becomes very small but positive. 1 divided by very small value, you get very large value, and since it's positive, you will get very large and positive. So this part looks like this. Here it tends to x-axis, or y is 0 is horizontal asymptote, and here it falls on this vertical asymptote. So at axis 3 there is a vertical asymptote. Let's consider this part. Also here we can see y, when we tend to this point from the left, y is very small but negative, and also here y is very small and negative, so 1 over y becomes very large and negative. And this specific point, since coordinates are given, can be calculated as 1 over y, so it's 1 over negative 3, so this point becomes negative 1/3 for y coordinate. And tails fall to negative infinity. Notice that it's not symmetrical, it's not like parabola. For some problems it may be, but here it's not necessary, it's just a curve. And this point, it's d prime, for example, it becomes 2 and minus 1/3, and this point is a local maximum here. And also this part, we can see that y becomes very small but positive, so here a graph tends to plus infinity. So this is a specific point, and actually this point also can be calculated. It becomes 0, 1 over 3, and it also will be y-intercept, and it becomes negative 1, 1/4. And notice that what about this tail? It falls to x-axis, it becomes very small but positive, 1 divided by very small but positive, so it becomes very large and positive, so it goes up and up here, and so it seems like this, and this point will be local minimum here. So it's something like this and something like this, and it becomes negative 1 and 1/4, and this 0, 1/3, and goes up to infinity, something like this. So it's the reciprocal function 1 over f. And now let's consider how to plot a graph of the derivative, or actually sketch the graph. So we can start with point, or actually we can review the properties. And first of all, by definition, stationary point is when or where derivative is equal to 0, and such points are candidates to be maximum or minimum, and it just points with horizontal gradient, because gradient of a tangent it's a derivative at a point, and in general it may be maximum, minimum, or neither. So stationary point by definition is just points where derivative is equal to 0, and so the mean derivative is 0, maximum derivative is also 0. So if derivative changes sign from minus to plus, because when function is decreasing, derivative is negative. When function is increasing, derivative is positive. So derivative positive, derivative is negative. So, and one method to check whether it's a point or maximum minimum to show that function or derivative changes sign. If from minus to plus it's minimum, from plus to minus it's maximum. Another method is to find the second derivative, and if second derivative at a point is positive, it means a function is concave up, and hence it's minimum. And if second derivative is negative at the point, it means shape is concave down, and it implies maximum. So it's called concave up, and second derivative is positive. Here second derivative is negative because it's concave down, and a point where second derivative is 0 is called point of inflection, and it's necessary condition. You also need to show that second derivative changes sign, or you need to show that just third derivative is not 0. It's enough to show that it's a point of inflection. And also, if second derivative is greater than 0, the first derivative is increasing function. They are related. And if second derivative is negative, the first derivative is decreasing function. So we can see these points, so maximum or minimum, or turning points, points where there is a horizontal tangent, it will be 0 for derivative. So at -1 and at at 2, derivative is 0. And let's consider this part. You can see that it's concave up, it's concave down, and somewhere here there is point of inflection, and it means that somewhere here second derivative is equal to 0, but second derivative is derivative of the first derivative, and if we consider the first derivative as some function, so second derivative, it becomes derivative of the first derivative, and if derivative is 0, it means maximum or minimum. So where second derivative is equal to 0, it means the first derivative has a maximum or minimum horizontal tangent. It will be stationary point for the first derivative, and also it's increasing function, and since it's increasing function, the first derivative is positive. So the first derivative is positive, and it's concave up, so the first derivative is increasing function, or the second derivative is positive. the second derivative is equal to 0 here, and it will be a point with horizontal tangent or stationary point for the first derivative, and it's a concave down, so the first derivative is decreasing function or second derivative is less than 0. Actually, y derivative is equal to 0. So it's at x minus 1, its derivative is 0, and we consider region to the left. It's the first derivative is positive and increasing here, decreasing here, and turning point somewhere here. So positive and decreasing, positive and increasing. So it looks like this, and it seems that it falls. And actually we know the derivative is a gradient of a tangent, so you can see that here tangent becomes more horizontal, and the more horizontal tangent is, the more closer to 0 gradient is. So we can suggest it falls to 0. So this region, you can see the first derivative is positive because function is increasing, and since it's concave up, derivative is increasing, so we can see it increases. At somewhere here we can see there is change in concavity, second derivative, but second derivative is derivative of the first derivative, and derivative of something, it's a point with horizontal tangent, and it will be turning point here, and at negative 1 it's 0. And again we can see this shape is concave down here, and again it becomes concave up here, and function is decreasing up to d, and function is decreasing, so function is decreasing, its derivative is negative, so up to d derivative is negative, and it's concave down firstly, and it means what? Second derivative is negative, or the first derivative is decreasing function, and here the first derivative is increasing function because it's concave up, and d it's at 2, increasing, decreasing, and at 2 it's 0, derivative is 0, so it looks like this. It's not clear where there is change in concavity, where this turning point for the derivative. And to the right from D we can see it's concave up and increasing function. It means derivative is positive, and since it's concave up, derivative is increasing function, so it goes up. Something like this. And actually it's a sketch, we don't know, we don't calculate exactly the coordinate of these points, turning points. We know exactly x intercepts, so it looks like this. And the second derivative, we can consider the same but with respect to the first derivative, or using just a function, and we need concavity, and we can see that somewhere here it's changing concavity, and somewhere here it's also change in concavity, so second derivative is 0 somewhere here and somewhere here, and it's actually horizontal tangent of the first derivative, second derivative is 0, and with respect to concavity, to the left it's concave up. And what does it mean? Concave up, second derivative is positive, and concave down, second derivative is negative. So it looks like this. And again, it's not a perfect parabola, it's something like this. Or with respect to the first derivative, we can see that to the left of a function, if we consider derivative to be a function, and second derivative will be derivative of this. So it's increasing, so it's positive, and here from 2 to plus infinity, we can see it's also increasing, so it's positive, and here it's negative. And turning point somewhere here. Okay, and now the opposite problem. It is given derivative, and we know to plot or sketch the function. And notice that we can draw a general shape, and we do not know where at which height it is exactly. So if you get some curve, for example, like this, you don't know where it is exactly. We need some specific points, and actually it is also given that function of 0 is equal to 0, so we should take it into account, and our graph should pass through this point. In general, it is given no points, just sketch general shape. So again, if derivative is equal to 0, what does it mean? It means stationary point, it means horizontal tangent. And we can see that to the left derivative is positive, to the right derivative is also positive. So to the left function is increasing, to the right function is also increasing, so it's not a turning point. And since it passes through 0, through the origin, so I draw like this, and here it appears that it's changing concavity, increases, and why it's changing concavity, you can see that derivative is decreasing. And what does it mean? It means second derivative is less than 0. It means concave down. Here the first derivative is increasing, it means second derivative is positive, it means concave up, so it looks like concave down to the left, concave up to the right. Something like this. And at 3 we can see again the first derivative is equal to 0, so again horizontal tangent, and we can see to the left derivative is positive, to the right minus, so derivative changes sign from plus to minus, so it increases to the right, decreases to the left, so it's a local maximum. And here it's a stationary point or turning point for the first derivative, and derivative of this is equal to 0 here, it's a stationary point, so second derivative is equal to 0 here. And what does it mean? It's the point of inflection. So somewhere here there is point of inflection, and so it's concave Now concave up, point of inflection, and maximum at 3. So this point is this point, and it may be not accurate, it must be with horizontal tangent here. Something like this. And I don't know where or coordinates of these points, where exactly they are, so we just sketch a graph. But we can show clearly that it's axis 1 here and axis 3 here. So it looks like this, and that's all for this question.